This section is section 9.2, and we look here at some examples of computing torque. We have done some of these in the last section. We looked at opening a door, and we mentioned using a screwdriver. We have not done these other examples, and so let me very briefly go back and say, what would we do if we want to open a door? Again, let's imagine our door. We put a force here, and I'll review that again quickly. Here's our force. Let's say it's equal to 10 newtons. It's at an angle of 30 degrees. It's at a distance out r. And we just worked the problem where r was equal to 2, force was 10 newtons, and our angle was 30 degrees. This meant that, of course, this is the total force here. This means that the force in the direction of the radius is going to be F cosine theta. And the one perpendicular, F perpendicular, is going to be F times sine theta. So our torque in this particular case is going to be R cross F, or magnitude of R, magnitude of F, times the sine of the angle. Of course, this is being the F perpendicular, which is going to be 2 times 10 times 0.5, which is the sine of 30 degrees, or 10 Newton meters. That gives us our torque. And we also talked about the fact that since this is in this direction, then in fact it is a torque that comes out of the board in the direction toward the reader, toward the camera. Now, if we were to do the same kind of thing with a screwdriver, we talked about the fact that if we had a screw or a bolt and we put a screwdriver in here, if the screwdriver has a tiny handle, we'll notice that we can't turn this screw, either tighten it or even loosen it. Why is that? Well, if we stop and think about it, it's because our hand, when we're pushing, and now I'm going to use another color here to imagine the screwdriver. Let's say our screwdriver is right here, and it's going down into that crevice where the blade of the screwdriver is. And as we try to turn the screwdriver, it has a very small handle. We're pushing here and we're pushing here with opposite forces with our hand, trying to turn that screwdriver, and it won't turn. Why is that? Because we can only apply so much force right here. But yet the radius is very small. If that radius is small, it's not going to give us enough torque. It is torque that we need to turn something, not force. That's totally obvious when you try to take something that has a very small radius and try to turn it. It won't work. But if we were to make this screwdriver very large, then when we grabbed it with our hand like this, then in fact it'd be very easy to turn it because the force, even though it's the same force, is applied at a much larger radius than it was here. So we'd only need maybe 1/4 as much force at this distance that we would need at this distance. Again, to unscrew something is going to require that we have a torque that is toward the camera, because we're going to turn it this way, so it's going to point upward. If we were going to tighten the screw or tighten the bolt into the system, then it would go into the system, and that's because it has what are called right-hand threads. In other words, the threads are associated with turning using the right-hand rule. We could very easily compute what the force would be there if we had to work that problem. Now I want to work another problem, which is a good example of a problem using torque. Let's imagine that we have a bridge. Down here we have water, banks of the bridge, and right here we have two supports, and in between there's no support at all. Now if we think about what force has to be put here, the upward force here and the upward force here, obviously this force, let's call this force 1, force 2, it's obvious because of the symmetry of the problem that force 1 plus force 2 must equal the weight of the bridge. The weight of the bridge can always be considered to be always exactly at the center of mass. Center of mass for a symmetric bridge would push downward, and it would have a downward force of m times g. I probably should use a capital M for a bridge. So F1 plus F2 is going to equal to m times g. Half of the weight of the bridge is going to be supported here, and the other half here. Now, let's look at that problem from the point of view of torques. And this is the way you think about a bridge problem. You imagine that this side of the bridge is a fixed axis, because it's certainly not going to rotate. And now you have two torques that are applied to the system. One torque up here, one torque here. Well, let's imagine that our bridge has a certain distance across, the length of a bridge. And now what we do is we want to compute these two torques relative to this axis. Whenever you compute a torque, you must compute it relative to some axis because you're going to use the distance r. What is torque? It's r times F perpendicular. Both of these F's are perpendicular, so we don't have to worry about an angle. But we have two of them, so what are they going to be? We're going to have to add these up, sum them. So what we have is, we have half of L with this much torque, so we have L over 2. That's our first R, or radius, as we come out to here before we look at the perpendicular force, and that force is mg. Then we look at, and let's call that negative because it's in the downward direction, and this we'll call upward because it's in the positive direction. We'll say plus F2. Now what is F2? What is the distance that it's being applied at? The answer is a distance L. Now what we want is we want equilibrium. So we want this torque to be equal to 0. In other words, we don't want the bridge to either fall at this end or to rise up out of the ground. We want it to be exactly stable. That will happen when the torques balance. In other words, there is no tendency to turn one way or the other. How do we do that? We set the total torque equal to 0. Then we can write this as L times F2 is equal to L over 2 times mg. I've just brought this to the other side of the equation. And now the L's cancel with each other, and we can see that F2 must be equal to 1/2 of mg, which is exactly what we knew back up here, because F1 and F2 were equal, so this is 2F2, and therefore F2 was 1/2 of mg. So our common sense would have told us what the answer was. However, let's suppose we have a more complicated situation, and now what we're going to do is we're going to take a truck. We're going to put this truck out here at a certain distance. And the truck has a mass small m. And it's going to be located at, let's say, 80% of this distance. So this is going to be a distance of 0.8 times L. And it has a mass small m. Well, what does it do with the torque? Well, that truck has a downward force, and this downward force is equal to small m times g. And it's being applied at this distance. So now, this is our no truck situation. And now we want to work a problem with our trucks. How do we do that? With truck. With the truck, we have, to redraw this very simply, we have an F2 pushing up here. We have a capital MG pushing down here. Here's our axis, or our center point. So we have two torques. Then we also have our truck sitting over here. This is a distance of L. This is a distance of L over 2. And this is a distance of 0.8 L. So now what are the sum of our torques? And remember, we're going to take up as positive. So we'd have the radius over, which is L. Torque total is going to be L, distance over, times F2. minus our bridge pushing downward, the distance L over 2 times mg. That's the radius over times the downward torque. Minus, we've got another torque here due to the truck, and it has a distance of 0.8 L, little m times g, because that's the force downward, or the perpendicular force to the radius here. And so we want that to be equal to 0. We can say, what do we get then? Well, we would get that L times F2 is going to be equal to L over 2 mg plus 0.8 L mg. Again, it turns out that the L's will cancel. We can factor out the g here, and we get F2. The force which we'll have to use to apply to push upward will be equal to m over 2 plus 0.8 m times g. And now you can see from that simple problem what force we would have to use. If the bridge, for example, had a mass of 200 tons, metric tons, and our truck had a mass of 4 tons, then all we have to do to find what F2 is to compute this, and we know what G is, so the answer would be F2 would be equal to 100, that's our 200 over 2, 200 over 2 gives us 100, plus 0.8 times 4 forms H 32, 3.2, quantity times G, or equivalently, G would be 10, so this would be equal to 103.2 times 10, or 1,032. And you'll notice here that we've got tons, and a ton is 1,000 kilograms, so that's 1,000 actual units, and that would be Newton meters for torque, for force, newtons. Because I've got mass times acceleration. Here's our mass in thousands of kilograms and our acceleration in 10. So I've added the other factor of 1,000 here because this is a ton, which is 1,000 kilograms. So this is basically going to be 1.032 million newtons that we require to hold up the truck and the bridge. We have talked before about how to find the center of mass in more complicated circumstances, but I'm going to reiterate it because it's covered here and it's very important. Again, I'm in 9.2, it's page B. If we have some strangely shaped object and we want to find the center of mass, what we can do is drill a hole at some point and hang it so that it's in equilibrium. When it does that, if we drop a plumb bob, that is a mass on the end of a string, right beside this hole where it's suspended, and draw a line along here, that line will necessarily include the center of mass, because the center of mass must swing exactly under here in order for there to be no torque. This line will always cross the center of mass. Then simply we can take this and do it in a similar way and suspend it about any other point. So we drill a point here, suspend it, get it to balance. Our plumb bob would go like this. The center of mass would be at those joined points like so. So if we take something like a sheet of plywood, it's very easy by using that methodology to find the center of gravity of an object. we simply hang it from the 2 points and look at the intersections of the verticals. And that's, of course, because hanging from this point here, the center of mass must be directly under it, otherwise it will give a torque one way or another to try to swing the object. I might mention that that problem that we had with the bridge is often given with two people carrying things also. So I'm going to go back over here and just mention that sometimes I've given this problem where you've got two students that are moving a couch, and on that couch you've got a TV set that's sitting at one end, and we know, of course, what the mass of the couch is, and we know the mass of the TV set. We know the position of the TV set relative to one of the carriers, and so our job is to figure out how much force each one of these people have to carry, have to push upward, in order to support their end of the couch. Of course, the total of the two is always going to be the total weight of, or force of gravity of the couch and the TV set. So if you compute one of the forces, you'll know the force of the other one very easily. Same thing goes with the truck here. When the truck is crossing, then in fact, when we compute this force, as we've done here, right here, the other force would be exactly the complement to give us the total gravitational force, capital M times G, small m times G. And you can see what that would be from right here. This other end would have to support m over 2 plus 0.2 m, quantity times G. We can solve that in our head. And that's what the other support down here would have to support the support beam here versus the support beam here.